In the summer of 2019, in a small office at the University of California, Santa Barbara, a physicist named Ahmed Al-Mehri sat staring at an equation that seemed to be telling him something impossible. The air conditioning hummed against the coastal heat outside, and through his window he could see the eucalyptus trees swaying in the Pacific breeze. But Al-Mehri wasn't looking at the trees. He was looking at a curve, a simple arc that rose and then fell, shaped something like a child's drawing of a hill, or perhaps like the trajectory of a ball thrown into the air. This curve, if his calculations were correct, represented the resolution to one of the most vexing paradoxes in the history of physics. It suggested that Stephen Hawking, the most famous physicist of the modern era, the man whose name had become synonymous with black holes themselves, had been wrong about something fundamental for nearly 50 years. Al-Mehri reached for his phone. He needed to call his collaborators. He needed someone else to check this. Because if this curve was real, if the mathematics held up under scrutiny, then they had just solved a puzzle that had tormented the greatest minds in theoretical physics for half a century. They had just demonstrated that information, the fundamental stuff of quantum reality, the irreducible description of everything that exists, is not destroyed when matter falls into a black hole, and that seemingly simple statement, that single scientific claim, had implications that rippled outward like waves from a stone dropped into still water, touching everything from the foundations of quantum mechanics to the nature of space-time itself, to questions about what reality fundamentally is and whether the universe, at its deepest level, makes any sense at all. To understand why Al-Mehri's hands might have trembled slightly as he dialed, to grasp why this particular curve on this particular afternoon represented perhaps the most significant breakthrough in theoretical physics in a generation, we need to travel back through time and space, back through decades of bitter scientific dispute, back to a moment in 1974 when a young Stephen Hawking first realised that black holes were not quite as black as everyone had assumed. Picture Cambridge, England, in the early 1970s. The university town is quieter then, its medieval spires and ancient colleges not yet overrun with tourists seeking glimpses of its famous residents. Along the River Cam, students pole their punts through water, the colour of weak tea, and in the Department of Applied Mathematics and Theoretical Physics, housed in a building of no particular architectural distinction, a revolution in our understanding of the cosmos is taking shape. Stephen Hawking is in his early 30s, already confined to a wheelchair by the motor neuron disease that doctors had once said would kill him within years. But his mind is sharper than ever, probing the most extreme objects the universe has to offer. Black holes, by 1974, were no longer merely theoretical curiosities. Einstein's general theory of relativity, published in 1915, had predicted their existence. Regions of space-time so severely curved by mass that nothing, not matter, not light, not information of any kind, could escape once it crossed a critical boundary called the event horizon. For decades, many physicists had dismissed these objects as mathematical artifacts, freakish solutions to Einstein's equations that surely couldn't exist in the real universe. But by the 1970s, observational evidence was mounting that black holes were real, that they lurked at the centres of galaxies and formed when massive stars collapsed at the ends of their lives. The question was no longer whether black holes existed. The question was what they actually were. Hawking had been working at the intersection of two great theories: general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which describes the behaviour of matter and energy at the smallest scales. These two theories had never been properly unified. They operated according to different rules, used different mathematical languages, and seemed in some deep sense incompatible with each other. But Hawking suspected that black holes, where gravity becomes extreme and quantum effects should become important, might offer clues to how the two frameworks could be reconciled. What he discovered instead was a crisis. Working through the quantum field theory calculations in that Cambridge office, surrounded by the gentle sounds of an English winter, radiators clicking, rain pattering against windows, the distant bells of college chapels marking the hours, Hawking found something that shocked him. Black holes, he realised, were not perfectly black. They radiated energy. Particles were being created at the event horizon and escaping into space, carrying energy away from the black hole. Over time, an almost inconceivable span of time, but time nonetheless. This radiation would cause the black hole to shrink. It would lose mass, and eventually, after eons that dwarfed the current age of the universe, the black hole would evaporate entirely, winking out of existence and leaving behind only the diffuse radiation it had emitted during its long death. The discovery was immediately recognized as one of the most important results in theoretical physics in decades. Hawking radiation, as it came to be called, represented the first concrete connection between general relativity and quantum mechanics. It showed that black holes were not eternal, that they had thermodynamic properties like temperature and entropy, that they were in some sense alive, or at least engaged in a slow process resembling death. But there was a problem that Hawking himself identified almost immediately, a problem that would consume his intellectual energies for the rest of his life, and that would remain unsolved for nearly half a century. The problem concerned information. In quantum mechanics, information is never truly destroyed. This is not a minor technical assumption, but rather one of the foundational principles of the theory, encoded in the mathematical structure of quantum mechanics itself. When you observe a quantum system, you can in principle trace back its history. The evolution of quantum states is what physicists call unitary. It preserves information through time, like a movie that can be run backward as well as forward. If you knew the complete quantum state of the universe at any moment, you could in principle calculate its complete quantum state at any other moment, past or future. Information might become scrambled, distributed, impossible to recover in practice, but it could never be truly erased. But Hawking radiation seemed to violate this principle. The particles emitted by a black hole, Hawking calculated, were perfectly thermal, random, featureless, containing no information about what had fallen into the black hole in the first place. Imagine throwing a book into a black hole. According to everything we knew about physics, the information encoded in that book, the arrangement of atoms, the patterns of ink, the words and ideas and stories should not simply disappear. But Hawking's calculations suggested that when the black hole finally evaporated, all that would remain was a bath of random thermal radiation, as featureless and information-free as the hiss of static on an untuned television. The book, and all information about it, would be gone forever. This was the black hole information paradox, and when Hawking presented it to the physics community, it landed like a bomb. To appreciate the gravity of this problem, you need to understand what physicists mean when they say that quantum mechanics would be undermined by information loss. They don't mean that certain predictions would be slightly off, or that some experimental results would need to be reinterpreted. They mean that the entire mathematical framework of quantum mechanics, the framework that successfully describes the behavior of atoms and molecules, that underlies our understanding of chemistry and material science, that forms the theoretical basis for lasers and transistors and MRI machines and everything else in our technological civilization, would be internally inconsistent. It would be like discovering that the rules of arithmetic allowed you to prove that 2 + 2 equals both 4 and 5. The theory would be broken in a fundamental way. It could not be salvaged with minor modifications. Everything would need to be rebuilt from the ground up. This is why the information paradox was not merely an academic puzzle, an interesting brain teaser for theoretical physicists to amuse themselves with during tea breaks. It was a genuine crisis, a sign that our two most successful physical theories were in irreconcilable conflict, and that one or both of them had to be wrong about something fundamental. Hawking's position was clear from the beginning, and he maintained it with characteristic stubbornness for decades. Information, he argued, really was destroyed in black holes. Quantum mechanics, at least in its standard formulation, was incomplete. The rules that applied to ordinary physics simply didn't hold in the extreme environment of a black hole's interior. Nature, Hawking insisted, was telling us something profound about the limits of quantum theory. But other physicists weren't so sure. Among the skeptics were some of the most formidable minds in the field, researchers who had devoted their careers to understanding quantum mechanics and who were not willing to abandon its foundational principles without overwhelming evidence. John Preskill, a physicist at Caltech with a reputation for choosing his intellectual battles carefully, was one of the most prominent doubters. He believed that information must somehow escape from black holes, that Hawking's calculations, while brilliant, must be missing something crucial. In 1997, Hawking and his collaborator Kip Thorne made a famous bet with Preskill. If information was indeed lost in black holes, Preskill would owe them an encyclopedia of his choosing, from which information could be retrieved at will. if information somehow escaped, Hawking and Thorne would owe Priskill the same. The bet crystallised the stakes, but it did nothing to resolve the debate. Throughout the late 1970s, the 1980s, the 1990s, physicists argued and calculated and published papers, but no consensus emerged. Some proposed that information might be encoded in the final burst of radiation emitted when a black hole reached the end of its evaporation. Others suggested that black holes might not evaporate completely, instead leaving behind some kind of remnant that stored the missing information. Still others argued that information might escape gradually throughout the evaporation process, encoded in subtle correlations in the Hawking radiation that were too complex to detect or calculate. None of these proposals was fully satisfying. Each created new problems of its own. The paradox deepened in 1993, when a young physicist named Don Page, working at the University of Alberta in Edmonton, Canada, published a paper that would prove crucial to the eventual resolution, though its importance would not be fully appreciated for more than 2 decades. Page had been Hawking's student at Cambridge, one of the brilliant young researchers who passed through the orbit of the famous physicist during his most productive years. Now he was working independently, applying the tools of quantum information theory to the black hole problem. Page's insight was deceptively simple. If information really was preserved, if Hawking radiation really did carry away information about what had fallen into the black hole, then there should be a specific pattern to how that information emerged. In the early stages of evaporation, when the black hole was large and the Hawking radiation was just beginning to stream away, the radiation would appear thermal and random, just as Hawking had calculated. But as the black hole shrank and more radiation was emitted, that radiation would need to become increasingly correlated with the radiation that had already escaped. The total entropy of the radiation, a measure of its randomness and inversely of how much information it contained, would follow a characteristic curve. It would rise at first as thermal radiation streamed out, but then at some point it would turn over and begin to fall. At the moment when the black hole had evaporated halfway, the entropy would reach a maximum and begin declining. By the time the black hole had completely evaporated, the entropy would have returned to its initial value, meaning that all the information that had ever fallen in would now be encoded in the outgoing radiation. Page drew this curve, the rise and fall of entropy during black hole evaporation, and it came to bear his name, the Page curve. It was what information preservation demanded. If black holes preserved information, their radiation had to follow the Page curve. If their radiation followed the traditional Hawking curve instead, entropy rising monotonically as thermal radiation poured out forever, then information was truly lost. But calculating the actual behaviour of Hawking radiation, demonstrating from first principles whether it followed the Page curve or the Hawking curve, was beyond the mathematical capabilities of any physicist in 1993. It was beyond the capabilities of any physicist in 2003, in 2013. The problem was simply too hard, the quantum gravitational effects too complex, the necessary theoretical tools not yet invented. And so the stalemate continued. In the years that followed, the physics community did not abandon the information paradox, but a kind of exhaustion settled over the field. Physicists had been arguing about black holes for 2 decades, and no one seemed able to land a decisive blow. Hawking remained convinced that information was lost. His opponents remained convinced it was preserved. Conferences were held, papers were published, bets remained unpaid. The paradox persisted like a low-grade fever, a sign of some underlying disease in the body of physics that no one knew how to treat. Then, in 2012, a new paper appeared that seemed to make things even worse. Ahmed Al-Mahiri, the same physicist who would later stare at that curve in Santa Barbara, was then a graduate student at the same institution. Working with Donald Marolf, Joseph Polchinski, and James Sully, he published an analysis arguing that the black hole information problem was even more severe than anyone had realized. Their paper, which became known by the acronym AMPS after its authors, argued that if information was truly preserved during black hole evaporation, then the interior of a black hole could not be what general relativity predicted. Instead of an observer falling smoothly through the event horizon, noticing nothing special as they crossed the point of no return, they would encounter a firewall, a violent surface of high-energy particles that would incinerate anything that approached. The smooth, empty interior of a black hole, the falling observer's ability to pass through the horizon without immediately dying was incompatible with the preservation of quantum information. This was a nightmare scenario. General relativity predicted smooth horizons, quantum mechanics demanded information preservation, and now it seemed that you couldn't have both. At least one of our foundational theories had to break down at the event horizon, and either option was unacceptable. If general relativity broke down, if horizons were truly violent firewalls, then Einstein's beautiful theory of gravity was wrong in a profound way. If quantum mechanics broke down, if information really was lost, then the foundation of all modern physics was shattered. There seemed to be no way out. The firewall debate raged through the mid-2010s. Hawking himself weighed in, proposing at one point that black holes might not have event horizons at all, that the boundaries we had imagined were somehow fuzzy or indeterminate. Conferences devoted entire sessions to the firewall problem. Physicists wrote papers attacking and defending the AMPS argument. Tempers occasionally flared, and still no consensus emerged. But beneath the sound and fury of the firewall debate, a quieter revolution was taking shape. To understand this revolution, we need to move to the other side of the country, to Princeton, New Jersey, where the Institute for Advanced Study sits on its wooded campus like a monastery of pure thought. Here, in the building where Einstein spent his final decades, a new generation of physicists was developing mathematical tools that would prove essential to cracking the information paradox. Among them was Juan Maldacena, an Argentinian physicist who had made one of the most important discoveries in theoretical physics of the late 20th century. In 1997, Maldacena had proposed something extraordinary, a precise mathematical equivalence between certain gravitational theories and certain quantum field theories without gravity. The details were technical. The equivalence related a theory of gravity in a particular curved space-time called anti-de Sitter space to a quantum field theory living on the boundary of that space-time. But the implications were profound. It meant that questions about gravity, about space-time, about black holes, could in principle be translated into questions about quantum fields. And quantum field theory was something physicists understood well. It was the framework underlying the standard model of particle physics, the most precisely tested theory in the history of science. Maldacena's correspondence, which came to be known as ADSE-CFT, or the holographic principle, offered a new way of attacking the information paradox. If the gravitational theory in the interior of anti-de Sitter space was exactly equivalent to a quantum field theory on its boundary, and if that quantum field theory preserved information, as all proper quantum theories must, then the gravitational theory must preserve information too. Black holes in anti-de Sitter space must somehow return their information. The paradox must have a resolution. This was encouraging, but it wasn't a proof. The holographic correspondence was a powerful conjecture, supported by a vast body of evidence, but it didn't explain how information escaped. It didn't provide a calculation of the page curve. It was like being told that a crime had been solved without being shown who committed it or how. Physicists wanted more than assurance. They wanted a demonstration. The demonstration would require new ideas about the nature of space-time itself, ideas that had been percolating through the theoretical physics community for years, but had not yet coalesced into a coherent picture. The key insight which emerged gradually through the work of many physicists was that space-time might not be fundamental. What we experience as the smooth fabric of space and time, the stage on which all physical events play out, might actually emerge from something deeper, from quantum entanglement, the strange correlations that bind quantum systems together across arbitrary distances. This idea, that space-time is woven from entanglement, sounds almost mystical, but it rested on precise mathematical relationships. When two quantum systems are entangled, they share information in a way that transcends their spatial separation. And there are formulas, derived by researchers including Shinsei Ryu and Tadashi Takayanagi, that relate the amount of entanglement between regions of a quantum system to the geometry of the space-time that emerges from it. These formulas, known as the Ryu-Takayanagi formula, and its generalizations, provided a bridge between the abstract world of quantum information and the concrete geometry of gravitational physics. By the late 2010s, all the pieces were in place. The holographic principle provided a framework. The entanglement geometry correspondence provided a tool. The firewall paradox provided urgency. What was needed was someone to put them together. And that brings us back to Santa Barbara, to Ahmed Almeri and his collaborators, to the summer of 2019 and the curve that seemed too good to be true. Almeri had been working with a small group of physicists, Donald Marolf, who had been his collaborator on the firewall paper, Henry Maxfield, a young British physicist with a gift for difficult calculations, and a rotating cast of other researchers drawn to the problem. They were not the only team working on these questions. Across the country and around the world, others were pursuing similar lines of thought. In Stanford, Jeff Pennington was developing related ideas. In Princeton, Muldacina and his collaborators were exploring the implications of entanglement for black hole physics. The field was converging, as fields sometimes do, on a single point. The breakthrough came through what might seem like an obscure technical development, a new formula for calculating the entropy of radiation emitted by an evaporating black hole. This formula, which would come to be called the island formula, or sometimes the quantum extremal surface prescription, built on the Ruta-Kayanagi formula, but generalized it in a crucial way. It allowed physicists to include contributions from what they called islands, regions of spacetime inside the black hole that, counterintuitively, contributed to the entropy of the radiation outside. The name islands came from the way these regions appeared in the calculations, as disconnected pieces of spacetime, isolated from the region where the radiation was being measured, yet somehow connected to it through the quantum structure of the theory. These islands emerged automatically from the mathematics. They weren't put in by hand or assumed into existence. They arose from the requirement that the entropy calculation be self-consistent, that the geometry of space-time and the quantum state of the radiation be compatible with each other. And when Almeri and his collaborators applied this formula to a black hole evaporating through Hawking radiation, they found something remarkable. In the early stages of evaporation, when the black hole was large, the formula gave the same answer as Hawking's original calculation. The radiation was thermal, random, informationless. But as the black hole shrank, as more radiation was emitted, the islands began to appear. And when they were included, the entropy of the radiation stopped growing. It turned over. It began to decrease. The curve that emerged from the calculation was the Page curve. For the first time in nearly 50 years of debate, someone had derived the Page curve from a controlled calculation, not assumed it, not argued for it philosophically, derived it from the mathematical structure of a quantum gravitational theory. Almeri checked his work. He checked it again. He called his collaborators. They checked it too. They found no errors. The calculation was correct. The Page curve was real. Information was preserved. The papers began to appear in 2019 and 2026, published by multiple groups who had arrived at compatible results through somewhat different routes. Almeri, Marolf, Maxfield, and their collaborators published their version. Pennington published his. Researchers at Stanford and Princeton and Cambridge and Tokyo contributed related work. The physics community, exhausted by decades of inconclusive debate, slowly began to realize that something fundamental had changed. The resolution was not what anyone had expected. It didn't involve firewalls. It didn't require abandoning either quantum mechanics or general relativity. Instead, it revealed something profound about the nature of space-time itself. That the interior of a black hole is not entirely separate from the exterior, that quantum effects can connect regions that appear geometrically disconnected, that the naive picture of a black hole as a region of spacetime from which nothing can escape is not quite right. The islands, in a sense, were the escaped information. They represented a way for the interior of the black hole to contribute to the quantum state of the radiation outside, even though no signal could classically travel from inside to outside. The mechanism was subtle, quantum mechanical in a deep way, but it was also mathematically precise. It could be calculated. It could be checked. It was not speculation or philosophy. It was physics. When word of these developments reached Stephen Hawking's former colleagues, there was a strange mix of emotions. Hawking had died in March 2018, just over a year before the island formula was published. He had spent the last decades of his life convinced that information was lost in black holes, that quantum mechanics needed to be modified, that his original 1974 calculation had revealed a fundamental truth about nature. In 2004, in a somewhat ambiguous concession, he had announced that he was giving up on his side of the bet with Preskill, presenting the Caltech physicist with a baseball encyclopedia. But Hawking had never been fully convinced, and his concession had been widely seen as provisional, a tactical retreat rather than a genuine capitulation. Now, a year after his death, it seemed that his opponents had been right all along. Information was preserved. The page curve was real. Quantum mechanics, in its standard unitary form, extended all the way down to the event horizon of a black hole and beyond. Hawking's greatest discovery, that black holes radiate, remained true and important, but his interpretation of that discovery, his insistence that information was destroyed, appeared to be wrong. The story, of course, is not so simple. Science rarely offers such clean narratives. There are caveats to the island formula, assumptions that have not been fully justified, aspects of the calculation that work cleanly only in special circumstances. The formula has been most rigorously applied to black holes in anti-de Sitter space, a mathematical idealization that differs in important ways from the universe we actually inhabit. Whether the same mechanisms apply to real astrophysical black holes, the ones drifting through our galaxy, the supermassive monsters at the hearts of quasars, remains an open question. And there are deeper puzzles that the island formula has not resolved. It tells us that information escapes, but it doesn't fully explain the mechanism. It reveals that space-time has a quantum structure that allows disconnected regions to be entangled, but it doesn't provide a complete theory of quantum gravity. It is a breakthrough, yes, arguably the most significant breakthrough in theoretical physics in decades, but it is also a signpost pointing toward mysteries still unsolved. The physicists who worked on these problems know this. They returned to their calculations after the initial excitement faded, looking for weaknesses, testing assumptions, extending the results to new situations. The island formula has spawned an entire subfield, with hundreds of papers exploring its implications for cosmology, for the nature of time, for the relationship between quantum mechanics and gravity, for questions about the fundamental nature of reality. In Santa Barbara, the eucalyptus trees still sway in the Pacific breeze, and the physicists still gather in seminar rooms to argue about black holes. The building where Almheri had his moment of realization still hums with air conditioning and the quiet sounds of thought. But something has changed. The intractable problem, the 50-year stalemate, has been broken. The paradox that Hawking himself had identified, that had consumed so much intellectual energy for so long, has been, if not fully solved, then at least partially tamed. And somewhere in the mathematics, in the curves and formulas and calculations, there is a story about the universe, about the nature of information, about what happens to the stories we tell and the words we write and the memories we hold when they fall into the darkest objects in the cosmos. That story turns out to be stranger than anyone had imagined, involving quantum connections across seemingly unbridgeable gulfs, involving the emergence of space-time itself from something deeper and more abstract. But it is also, in some fundamental sense, reassuring. The universe, it seems, does not forget. The information falls in, and the information comes out, and nothing is truly lost. This is the story of how we learned that truth, of the decades of struggle and the sudden breakthrough, of the men and women who devoted their careers to understanding the most extreme objects in the universe, and who finally, after so long, found a piece of the answer. It is a story that begins with Hawking, in his wheelchair in Cambridge, staring at equations that told him black holes glow, and it continues to this day, in offices and seminar rooms around the world, where the next generation of physicists is working to understand what the island formula truly means. The paradox was formulated. The paradox was fought over. The paradox at last began to yield. And the universe, it turned out, was stranger and more beautiful than even Hawking had dared to imagine. The path to that breakthrough stretches back further than most people realise, winding through decades of incremental progress, failed attempts, and half-understood hints that something profound was lurking in the mathematics. To understand how Almheri and his collaborators finally cracked the paradox, we need to follow that path, to trace the intellectual lineage that made the island formula possible. It begins, in many ways, not with black holes at all, but with a deceptively simple question about quantum information. The question is this: if you take a quantum system and divide it into two parts, how much information does one part contain about the other? This might seem like an abstract concern, the kind of puzzle that occupies mathematicians and has no bearing on physical reality. But it turns out to be absolutely fundamental to understanding how information behaves in the universe, and it would eventually provide the key to unlocking the black hole information paradox. The concept at the heart of this question is called entanglement entropy. We've encountered it already in passing, but now we need to understand it more deeply, because without it, nothing that follows will make sense. Imagine a pair of particles created together in a process that links them quantum mechanically. These particles fly apart, travelling to opposite ends of a laboratory or opposite ends of a galaxy. Despite the distance between them, they remain connected in a way that has no classical analogue. If you measure one particle and find it spinning clockwise, the other will instantly be spinning counterclockwise, no matter how far apart they are. This is entanglement, and it is one of the most counterintuitive features of quantum mechanics. But entanglement is not just a binary property, something that either exists or doesn't. It comes in degrees. Systems can be more or less entangled, and the amount of entanglement can be precisely quantified. The measure of this quantity is entanglement entropy. The name is no accident. Just as ordinary entropy measures the disorder of a system, or equivalently the amount of information needed to fully describe its microscopic state, entanglement entropy measures how much quantum information is shared between two parts of a system. If two systems are completely unentangled, knowing everything about one tells you nothing about the other, and the entanglement entropy is zero. If they are maximally entangled, the two systems are so deeply connected that neither can be described independently, and the entanglement entropy is large. This concept was developed primarily in the context of quantum information theory, a field that emerged in the 1980s and 1990s as physicists began to understand how quantum mechanics could be used to process and transmit information. Researchers like Charles Bennett, Gilles Brassard, and others realized that entanglement was not just a curiosity, but a resource, something that could be harnessed for tasks like quantum cryptography and quantum teleportation. Understanding how to quantify entanglement became essential, but the connection to gravity and black holes emerged from an unexpected direction. The study of quantum field theory, the mathematical framework that describes particles and forces at the most fundamental level. In quantum field theory, empty space is not truly empty. The vacuum seethes with activity, with virtual particles flickering in and out of existence, with quantum fields fluctuating even when no real particles are present. These vacuum fluctuations are entangled across space. If you draw an imaginary boundary through the vacuum and ask how entangled the fields on one side are with the fields on the other, you get a finite answer, and that answer turns out to have a remarkable property. The entanglement entropy of vacuum fluctuations is proportional to the area of the boundary, not the volume of the regions involved, the area of the surface that divides them. This result, derived through careful calculations in quantum field theory, echoed something that physicists had known about black holes since the 1970s, that the entropy of a black hole is proportional to the area of its event horizon. Bekenstein had proposed this, Hawking had confirmed it, and it had seemed like a peculiar coincidence, a quirk of black hole physics. But here it was again, in a completely different context. The entropy of entanglement follows an area law. This parallel demanded explanation. Why should black hole entropy and entanglement entropy both scale with area? Was there a deeper connection lurking beneath the surface? The first person to seriously pursue this connection was a physicist named Mark Srednicki, working at the University of California, Santa Barbara in the early 1990s. Srednicki showed explicitly that the entanglement entropy of quantum fields across a boundary is infinite in the continuum limit, but can be regulated to give a finite answer proportional to area. His work established that the area law for entanglement entropy is a generic feature of quantum field theory, not something special about black holes, but this raised as many questions as it answered. If ordinary entanglement entropy satisfies an area law, and black hole entropy satisfies an area law, are they the same thing? Is black hole entropy actually entanglement entropy in disguise? And if so, entanglement between what and what? These questions percolated through the theoretical physics community for years, generating papers and arguments and partial answers. Different researchers proposed different interpretations. Some argued that black hole entropy was the entanglement entropy between the quantum fields inside the event horizon and those outside. Others suggested that the connection was more subtle, involving degrees of freedom we don't yet fully understand. The person who would take these ideas furthest was Juan Maldacena, and his contribution would reshape the entire landscape of theoretical physics. Maldacena was born in Buenos Aires in 1968, during a period of political turbulence in Argentina. he showed early aptitude for physics and eventually made his way to Princeton University for his graduate studies. There, under the guidance of Curtis Callan, he began exploring the connections between string theory and black holes. String theory, which had emerged in the 1970s and matured through the 1980s, offered a radically different picture of fundamental reality. Instead of point particles, the basic objects were tiny vibrating strings. The different vibration modes of these strings corresponded to different particles, and the theory naturally incorporated gravity, something that had proven impossible to achieve in conventional quantum field theory. By the 1990s, string theory had become one of the leading candidates for a theory of quantum gravity, and researchers were using its mathematical machinery to attack problems that had seemed intractable. Maldacena was particularly interested in a class of objects called D-branes, extended surfaces on which the endpoints of open strings could terminate. D-branes had interesting gravitational properties, and by stacking many of them together, you could create configurations that looked very much like black holes. Maldacena realized that there were two different ways to describe these configurations, one in terms of the strings and branes themselves, and another in terms of the curved space-time geometry they created. Working through the mathematics, he made a stunning discovery. In certain cases, these two descriptions were not just similar, but exactly equivalent. A theory of quantum gravity in a particular curved space-time was mathematically identical to a quantum field theory without gravity, living on the boundary of that space-time. The physics inside the curved space could be completely captured by the physics on its boundary, like a hologram encoding a three-dimensional image on a two-dimensional surface. This was the AD-CFT correspondence, announced in a short paper in late 1997, and it would revolutionize theoretical physics. The name comes from the specific geometries involved. ADA stands for anti-de Sitter space, a particular solution to Einstein's equations describing a universe with a negative cosmological constant. Unlike our own universe, which appears to have a positive cosmological constant and is therefore expanding at an accelerating rate, anti-de Sitter space curves back on itself, creating a kind of cosmic box with a boundary at infinity. CFT stands for conformal field theory, a special class of quantum field theories that have a high degree of symmetry. Maldacena's conjecture stated that string theory in anti-de Sitter space is exactly equivalent to a conformal field theory living on the boundary of that space. The two descriptions use completely different languages, involve completely different concepts, but they describe exactly the same physics. Every question you can ask in one theory has a translation into the other theory, and the answers match perfectly. This duality had profound implications for the black hole information paradox. Black holes can form in anti-de Sitter space, and when they do, they have a dual description in terms of the boundary conformal field theory. But conformal field theories are ordinary quantum theories, governed by the standard rules of quantum mechanics. They are unitary, meaning they preserve information. If the black hole physics is equivalent to CFT physics, then the black hole must also preserve information. This was a powerful argument, but it was also somewhat indirect. It relied on the assumed truth of the duality, which had not been proven from first principles. And it didn't explain how information was preserved, what mechanism allowed information to escape from the black hole, what happened to the arguments that Hawking had marshalled in favour of information loss. The duality suggested that information survives, but it didn't reveal the details. In the years following Maldacena's discovery, physicists scrambled to understand the implications of AD-CFT for black holes and information. One of the most important developments came from two researchers at Stanford, Shinsei Ryu and Tadashi Takayanagi. Ryu and Takayanagi were interested in the area law for entanglement entropy, and its connection to gravity. In the boundary CFT, you could compute entanglement entropy using the standard methods of quantum field theory. In the bulk AD space, you had gravity and curved space-time. Was there a way to translate entanglement entropy from one description to the other? Working through the mathematics, they proposed a remarkably simple formula. To calculate the entanglement entropy of a region in the boundary theory, you should find the minimal surface in the bulk that shares its boundary with that region, and then compute the area of that surface. The entanglement entropy, they claimed, was proportional to this area, with a proportionality constant determined by Newton's gravitational constant. This Ryu-Takayanagi formula, published in 2006, provided a direct geometric interpretation of entanglement entropy. In the gravity picture, entanglement was literally measured by areas of surfaces. The more entangled two regions were, the larger the minimal surface connecting them. The formula was beautiful, but it was also puzzling. It seemed to work only for static situations where nothing was changing in time. When black holes evaporated, when quantum systems evolved dynamically, the minimal surface could change in complicated ways. Hawking radiation was an inherently time-dependent process, and the Ru-Takayanagi formula didn't directly address it. Extending the formula to dynamical situations required new ideas. In 2007, Veronica Hubany, Mukund Rangamani, and Tadashi Takayanagi proposed a generalization that worked for time-dependent geometries. Instead of minimal surfaces, they considered extremal surfaces, which could extend through time as well as space. This HRT formula, named after its authors, was more powerful but also more complicated. These tools gave physicists new ways to think about entanglement and gravity, but they still hadn't directly confronted the information paradox. The paradox was about what happens as a black hole evaporates, about the relationship between the radiation emitted early and the radiation emitted late. To address this, researchers needed to track how entanglement entropy changed throughout the evaporation process. This is where the Page curve enters the story. Don Page, the same physicist who had worked with Hawking in the 1970s, had been thinking about the information paradox for a long time. In 1993, he published a paper that would become increasingly important as the years went by. The paper asked a simple question. If black hole evaporation is a unitary process, meaning it preserves information, what should happen to the entanglement entropy of the radiation? Page modelled the black hole and its radiation as a combined quantum system. At the beginning, before any radiation is emitted, the entanglement entropy of the radiation is zero, because there is no radiation. As the black hole emits Hawking radiation, the entropy of the radiation increases. Each photon carries some entanglement with the black hole, and the total entanglement grows. But here's the key insight. If the process is unitary, this growth cannot continue forever. The total system, black hole plus radiation, remains in a pure quantum state, because unitary evolution preserves purity. As more and more of the black hole's degrees of freedom are transferred to the radiation must eventually transition from being entangled with the black hole to being entangled with itself. The entanglement entropy must peak and then start to decrease. Page calculated when this transition should happen. He found that the entropy of the radiation should reach a maximum at roughly the halfway point of the evaporation, when the black hole has lost about half of its initial entropy. After this point, which became known as the Page time, the entropy should decrease, eventually returning to zero when the black hole is completely evaporated. The resulting curve, entropy plotted against time, rises and then falls, shaped roughly like an inverted V or a smooth arch. This is the Page curve, and it became the signature of unitary evaporation. If black holes preserve information, the entropy of the radiation must follow this curve. But Hawking's calculation predicted something entirely different. In Hawking's analysis, the radiation was exactly thermal, and its entropy simply increased monotonically throughout the evaporation. There was no turnover, no peak, no return to zero. The entropy kept climbing even as the black hole shrank, eventually exceeding any reasonable bound when the black hole became microscopic. This was the information paradox in entropic form. Hawking's curve and Page's curve disagreed dramatically, and they couldn't both be right. For decades, the challenge was clear. Derive the Page curve from a gravity calculation. Show, using the laws of physics applied to black holes, that the entanglement entropy of Hawking radiation follows Page's prediction rather than Hawking's. Accomplish this, and you would have demonstrated that information is preserved. The problem was that no one could do it. Every gravity-based calculation seemed to reproduce Hawking's result, an ever-increasing entropy that violated unitarity. The tools weren't there. The understanding wasn't there. The Page curve remained a theoretical prediction, a benchmark against which any resolution of the information paradox would have to be measured. The breakthrough would require new ideas, new mathematical techniques, and a willingness to challenge assumptions that had seemed fundamental. It would require physicists to rethink what they meant by the interior of a black hole, to reconsider the boundaries between systems, to embrace the strange quantum connections that the island formula would eventually reveal. But before that breakthrough could occur, another conceptual development was necessary. Physicists needed to understand more deeply how space-time itself could emerge from quantum entanglement, how the smooth fabric of general relativity could arise from the discrete dance of quantum information. This understanding would come from an unexpected direction: the study of quantum error correction. In the early 2010s, researchers at the intersection of quantum information theory and high-energy physics began to notice curious parallels between the structure of ADS-CFT and the codes used to protect quantum information from errors. When you store quantum data in a noisy environment, errors can accumulate and corrupt the information. Quantum error-correcting codes spread the information across many degrees of freedom in such a way that local errors can be detected and corrected without destroying the encoded data. Daniel Harlow, then a graduate student at Stanford, and his collaborator Fernando Pastowski, along with Benny Yoshida and John Preskill, realized that the way bulk information is encoded in the boundary CFT bears a striking resemblance to these error-correcting codes. The bulk physics is redundantly encoded in the boundary, distributed across many boundary degrees of freedom in a way that protects it from local perturbations. This wasn't just a loose analogy, but a precise mathematical correspondence. This perspective shifted how physicists thought about the emergence of space-time. The bulk of ADS space, with its extra dimension and its gravity, was not fundamental but emergent. It arose from the entanglement structure of the boundary theory, from the web of quantum correlations between different parts of the CFT. Space-time, in this view, was stitched together by entanglement. Van Ramsdonk, a physicist at the University of British Columbia, made this intuition vivid with a simple thought experiment. Take 2 copies of a CFT and entangle them maximally. The corresponding bulk geometry is a wormhole, a bridge connecting 2 separate regions of space-time. Now gradually reduce the entanglement between the 2 theories. As you do so, the wormhole narrows, becoming longer and thinner. In the limit of zero entanglement, the wormhole pinches off entirely, and the 2 regions of space-time become disconnected. This result, summarized in the slogan ER equals EPR, popularized by Maldacena and Leonard Susskind, suggested that Einstein-Rosen bridges, the wormholes of general relativity, were equivalent to Einstein-Podolsky-Rosen correlations, the quantum entanglement of particles. Space-time connectivity and quantum entanglement were 2 faces of the same phenomenon. These ideas were beautiful but also deeply strange. They implied that the seemingly rigid structure of space-time, the stage on which all physics plays out, was actually a derivative concept, arising from something more fundamental. Quantum entanglement came first, and space-time emerged from it. This inversion of the usual hierarchy, where space-time contains quantum fields, suggested that the rules governing quantum information might be more fundamental than the rules governing geometry. And if that was true, then perhaps the black hole information paradox had been approached from the wrong direction all along. Perhaps the solution lay not in modifying quantum mechanics, or in accepting information loss, but in understanding how the geometry of space-time itself could reorganize in response to quantum constraints. This was the intellectual landscape in the late 2010s, a ferment of ideas about entanglement, geometry, emergence, and information. The pieces were on the board, but they had not yet been assembled into a coherent picture. That assembly would require a specific calculation, a concrete result that brought all these threads together. The calculation would be performed in the offices of UCSB, in the quiet hours when the Pacific winds died down, and the only sounds were the hum of computers and the scratch of chalk on blackboard. It would involve techniques from quantum field theory, from string theory, from quantum information science. It would draw on decades of prior work while introducing something genuinely new, and when it was complete, it would produce a curve, an entropy as a function of time, that matched not Hawking's prediction but Page's. The Page curve, the signature of unitarity, would emerge from a gravity calculation for the first time. The breakthrough was close now, waiting to be discovered. The paradox that had plagued physics for nearly half a century was about to yield its secrets. In Santa Barbara, in Princeton, in Stanford, in universities and research institutes around the world, the next chapter of this story was about to be written. The calculation that would change everything began, as many revolutions do, with a question that seemed almost too simple to be profound. Ahmed Al-Miri, a physicist from the United Arab Emirates who had trained at Stanford and was now working at the Institute for Advanced Study in Princeton, had been wrestling with a puzzle that grew directly from the firewall debate he had helped ignite years earlier. The Amos paradox had shown that something had to give, that the conventional assumptions about black holes could not all be maintained simultaneously. But the firewall conclusion, dramatic as it was, felt wrong to many physicists. It seemed to violate the equivalence principle at the heart of general relativity, the principle that had guided Einstein to his greatest insights. There had to be another way. Almehri found himself returning again and again to the Ryu-Takayanagi formula, that elegant prescription for computing entanglement entropy in holographic theories. The formula had a geometric simplicity that physicists had learned to trust. When something in theoretical physics takes such a clean mathematical form, it often signals deep truth. But the formula had been developed in the context of static situations, configurations that did not change with time. Black holes, especially evaporating black holes, were anything but static. They were dynamic, evolving systems in which the very geometry of space-time was in flux. Could the Ryu-Takayanagi formula be extended to handle such situations? Others had worked on this problem. Veronica Hubany and Mukund Rangamani, working with Ryu and Takayanagi, had developed a covariant version of the formula that could handle time-dependent geometries. Their prescription, known as the HRT formula, replaced the minimal surface of the original with an extremal surface, one that satisfied certain optimization conditions even in dynamically evolving spacetimes. This was progress, but it still was not quite enough. The HRT formula worked beautifully in many contexts, but when applied to evaporating black holes, it continued to give Hawking's answer. The entropy just kept rising indefinitely, without ever turning over to follow the Page curve. The problem was subtle but critical. In the standard application of these formulas, physicists calculated the entropy of the radiation by finding the appropriate surface in the bulk geometry and computing its area. But for an evaporating black hole, the only available extremal surface seemed to be one that simply tracked the growth of radiation. There was no mechanism in the calculation that would cause the entropy to decrease as the black hole shrank. Something was missing. The missing ingredient would come from an unexpected direction, from the gravitational path integral, a formalism that Richard Feynman had pioneered for quantum mechanics, and that had been extended to quantum gravity with varying degrees of rigour and success. The path integral approach to quantum gravity was notoriously difficult, plagued by divergences and ambiguities that made calculations uncertain. But it also had a power that other approaches lacked. It could capture contributions from configurations that classical reasoning would overlook, configurations that might be individually improbable, but that summed together could dominate the physics. Geoffrey Pennington, a young physicist who had recently completed his doctorate at Stanford under Patrick Hayden, was thinking about these issues in late 2018 and early 2019. Pennington had an unusual combination of interests, having worked on both quantum gravity and quantum information theory. He understood the language of entanglement and entropy that quantum information theorists used, but he also knew how to think about geometry and gravity in the way that string theorists did. This dual fluency would prove essential. Pennington was focused on a specific question. What happens when you try to compute the entropy of Hawking radiation using the gravitational path integral? The standard approach would seem to give Hawking's answer, the ever-increasing entropy that signalled information loss. But Pennington suspected that the standard approach was missing something. The gravitational path integral, properly understood, might include contributions from geometries that changed the answer dramatically. The key insight came from thinking carefully about what physicists call replicas. In quantum field theory, there is a standard trick for computing entanglement entropy called the replica method. Instead of calculating the entropy directly, which involves a logarithm and is mathematically awkward, you calculate a related quantity called the Renyi entropy for integer values of a parameter n. This quantity involves taking n copies of your system, the replicas, and computing certain correlation functions between them. Then, through a process of analytic continuation, you take the limit as n approaches 1, recovering the true entanglement entropy. The replica trick had been used in gravity before. Lukowicz and Maldacena had shown how it could be used to derive the Ryu-Takayanagi formula, providing a deeper understanding of why that formula worked. But when Pennington and, independently, a group at Santa Barbara began applying replica methods to evaporating black holes, they discovered something remarkable. The gravitational path integral included contributions from geometries in which the replicas were connected in unexpected ways. These connected replica geometries, sometimes called replica wormholes, changed the calculation fundamentally. The Santa Barbara group consisted of Ahmed Almeri, who had moved there from Princeton, together with Thomas Hartmann, Juan Maldacena, and Edgar Shagulian. They were approaching the same problem from a slightly different angle, but converging on the same conclusions. The atmosphere in Santa Barbara during those months was electric, the kind of intellectual ferment that occurs when multiple researchers sense that something important is within reach. The campus of the University of California, Santa Barbara, sits on a bluff overlooking the Pacific Ocean, and the physicists working there often took breaks to walk along the shore, discussing ideas against the backdrop of crashing waves and wheeling seabirds. But much of the work happened late at night, in offices filled with blackboard calculations that sprawled across multiple panels, intricate diagrams of geometries and surfaces and radiation fields. What both groups found was that when you properly account for all the contributions to the gravitational path integral, a new term appears in the formula for entanglement entropy. This term involves a surface that sits not at the boundary of the radiation region, as in the standard calculation, but deeper in the bulk geometry, in a region that might seem disconnected from the radiation entirely. This surface came to be known as the quantum extremal surface, and its properties would resolve the paradox that had persisted for decades. The quantum extremal surface prescription was a generalization of the Ryu-Takayanagi formula. Instead of simply minimizing the area of a surface anchored to a boundary region, you now had to extremize a more complex quantity, the area of the surface plus the entropy of quantum fields on one side of it. This quantum correction might seem like a small modification, but its effects were dramatic. In the context of an evaporating black hole, there were now two competing surfaces that could contribute to the entropy calculation. The first surface was the one that had dominated in previous calculations, a surface that simply tracked the growth of Hawking radiation and gave an ever-increasing entropy. But there was now a second candidate surface, one that sat just outside the event horizon of the black hole, enclosing the interior. For this second surface, the area term was roughly the area of the black hole horizon itself, which decreased as the black hole evaporated. The quantum field theory contribution added some entropy from the radiation, but crucially, this contribution was bounded. The prescription for computing the actual entropy was to take the minimum of these two candidate surfaces at any given time. Early in the evaporation process, when the black hole was still large and had emitted only a small amount of radiation, the first surface gave the smaller value. The entropy of the radiation followed Hawking's prediction, growing steadily with each emitted quantum. But as time went on and the black hole shrank, there came a moment when the two surfaces gave equal values. Beyond this point, the second surface, the one near the horizon, gave the smaller value and dominated the entropy calculation. This transition, this exchange of dominance between surfaces, produced exactly the behaviour that Page had predicted decades earlier. The entropy of the radiation increased initially, following Hawking's expectation, but then reached a maximum and began to decrease, eventually returning to zero when the black hole had fully evaporated. The Page curve, that signature of unitary quantum evolution, emerged from a gravity calculation for the first time in history. The papers presenting these results appeared in rapid succession in 2019. Pennington's paper, titled Entanglement Wedge Reconstruction and the Information Paradox, was posted to the physics preprint server in May. The Santa Barbara group's paper, The Entropy of Hawking Radiation, appeared in September. Both papers reached the same essential conclusions through somewhat different routes, a convergence that strengthened confidence in the result. The physics community reacted with a mixture of excitement and caution. The result was so significant and had been sought for so long that many physicists wanted to scrutinize it carefully before accepting its implications. What made the result so compelling was not just that it produced the Page curve, but how it did so. The key ingredient was a region of space-time that the calculation revealed to be associated with the radiation, even though it appeared, from a naive geometric perspective, to be part of the black hole interior. This region, bounded by the quantum extremal surface near the horizon, came to be known as the island. The island was a conceptually startling feature. It represented a portion of the black hole interior that, according to the principles of holography and quantum information, was actually encoded in the Hawking radiation outside the black hole. The radiation did not merely carry subtle correlations, as Page had envisioned, but was in some sense a complete description of the island region. The interior of the black hole, or at least this portion of it, was redundantly encoded, once in the black hole itself and once in the radiation. This redundancy was precisely analogous to the redundancy in quantum error-correcting codes, the same mathematical structure that Harlow, Postowski, Preskill and Yoshida had identified in the relationship between bulk and boundary and ADS-CFT. The implications were profound. When the island appeared in the calculation, it changed the answer for the entropy of the radiation from Hawking's prediction to Page's. The information that seemed to be trapped behind the event horizon was actually accessible, in principle, from the radiation. There was no need for information to be destroyed at the singularity or to survive in some Planck-scale remnant. The information was out, encoded in the radiation in a manner so complex and scrambled that no realistic measurement could decode it, but there in principle nonetheless. The name island formula came to describe the generalized prescription for computing entanglement entropy that these calculations revealed. The formula stated that the entropy of a region R is given by the minimum over all possible islands I of the following quantity, the area of the boundary of the island divided by 4 times Newton's constant, plus the von Neumann entropy of the quantum fields in the combined region R union Y. When no island contributes, you get the standard quantum field theory answer. But when an island does contribute, the answer can change dramatically, as it does in the case of an evaporating black hole. What was particularly striking about the island formula was its generality. Although it had been derived in the context of specific models, there was strong evidence that it reflected something universal about quantum gravity. The formula made sense in a wide variety of contexts and gave sensible answers in situations where other approaches had failed. It suggested that the relationship between entanglement and geometry, which had been developing since the work of Ryu and Takayanagi, was even deeper than previously understood. Space-time regions that appeared disconnected from a naive geometric perspective could be connected through quantum entanglement, and this connection had physical consequences that could be calculated. The physicists involved in this breakthrough knew they had achieved something significant, but they were also aware that many questions remained. The calculations had been performed in simplified models, particularly in 2-dimensional models of gravity known as Jakob-Teitelbaum gravity, which were mathematically tractable, but lacked some features of the real 4-dimensional universe. Could the results be extended to more realistic settings? The evidence suggested yes, but rigorous proofs were still forthcoming. There was also the question of mechanism. The island formula told you how to compute the right answer, but it did not provide a fully satisfying physical picture of how information gets out of a black hole. The radiation carries information, encoded in correlations so complex they appear thermal to any local measurement. But what physical process creates these correlations? The answer seemed to lie in the non-perturbative effects captured by the gravitational path integral, the replica wormholes that connected different copies of the geometry. But understanding these effects intuitively, in a way that could be explained without advanced mathematics, remained challenging. One helpful perspective came from thinking about the experience of different observers. An observer falling into the black hole would notice nothing unusual at the horizon, exactly as the equivalence principle demands. They would see smooth space-time, perhaps some mild tidal forces as they approached, but no firewall or violent disruption. Yet an observer remaining outside the black hole, collecting and analysing the Hawking radiation over billions of years, would in principle be able to reconstruct information about what fell into the black hole long ago. There was no contradiction, because these two descriptions applied to complementary situations that could never be directly compared. The observer who falls in cannot bring their information back out to compare notes with the observer who stayed outside. This complementarity, an idea that had been around since the 1990s, was given new precision by the island formula. The interior of the black hole was real and accessible to the falling observer, but it was also encoded in the radiation, and accessible, at least in principle, to the exterior observer. These were not contradictory facts, but complementary descriptions of the same quantum state. The island formula provided the mathematical bridge between them. In the months following the initial papers, a flurry of activity swept through the theoretical physics community. Dozens of papers explored different aspects of the island formula, testing it in various contexts, extending it to new situations, probing its limitations. the calculations were extended to higher dimensions, to different types of black holes, to cosmological settings. In each case, the formula seemed to give sensible results, building confidence that it captured something true and fundamental. One particularly important extension involved eternal black holes rather than evaporating ones. An eternal black hole in ADS space-time is a theoretical construct, a black hole that has existed forever and will continue to exist forever because it is in thermal equilibrium with its environment. For such a black hole coupled to an external bath that collects radiation, the island formula could be applied, and it again produced the expected behaviour. The entropy of the bath region started small, grew as radiation accumulated, and eventually reached a constant value consistent with the entropy of the black hole itself. The presence of the island in the calculation was essential to obtaining this result. Another important development was the derivation of the island formula from more fundamental principles. While the initial calculations had discovered the formula by analysing specific examples, subsequent work showed how it could be understood as a consequence of gravitational replica tricks applied systematically. This gave the formula a firmer theoretical foundation and helped clarify why it worked. There was also growing appreciation for the role of random matrix theory in these calculations. When physicists analysed the detailed statistics of energy levels in the boundary theory's dual to gravitating systems, they found patterns characteristic of quantum chaotic systems, patterns that random matrix theory had been developed to describe. These patterns were intimately connected to the appearance of islands and the restoration of unitarity. The gravitational path integral, summed over all geometries including replica wormholes, reproduced exactly the statistics expected from random matrix theory. This connection between gravity, chaos, and random matrices was unexpected and deep, suggesting new directions for research. The theoretical physics community, often divided into camps focused on different approaches and techniques, found itself converging on a shared set of questions and methods. String theorists, quantum information theorists, condensed matter physicists working on quantum chaos, and researchers studying the mathematical structure of quantum field theory all found their work intersecting in surprising ways. The island formula stood at the crossroads, a concrete result that drew on insights from many disciplines and pointed toward a more unified understanding. But even as the technical work progressed, there was awareness that the deepest questions remained open. The island formula worked within the framework of the ADS-CFT correspondence, a setting with special properties that made calculations tractable. Whether similar results held in de Sitter space, the geometry that describes our actual expanding universe, was unclear. The relationship between the island formula and a complete theory of quantum gravity, whatever that might turn out to be, was still mysterious. The formula seemed to be telling us something true about the world, but interpreting that message fully would require insights that had not yet been achieved. What was clear, however, was that a page had been turned. The black hole information paradox, that stubborn challenge that had resisted resolution for nearly 50 years, had yielded ground. Not all the questions were answered, but a major barrier had fallen. The page curve, long held up as the criterion for a satisfactory resolution, had been derived from a calculation involving gravity. Information was preserved. Unitarity held. The universe, at least in these simplified models, followed the rules that quantum mechanics demanded. Stephen Hawking had passed away in March 2018, just a year before these results began to emerge. In his final decades, he'd modified his position on information loss, conceding in 2004 that information was probably preserved after all, though never quite accepting that his original calculation had been wrong. He had believed that quantum gravity effects would somehow resolve the paradox, that the calculation of ever-increasing entropy was valid as far as it went but missed something important. In a sense, he was right. The missing piece was the island, a contribution that his original calculation, groundbreaking as it was, had not included. The semi-classical approximation that Hawking had used was valid in its regime but incomplete. A fuller treatment, one that included non-perturbative gravitational effects, changed the answer. Whether Hawking would have been satisfied by these results, whether he would have embraced the island formula as the resolution to the paradox he had created, is impossible to say. Some of his former students and collaborators suspected he would have found the approach too tied to specific theoretical frameworks, too dependent on ADS-CFT, to be fully satisfying. Others believed he would have been delighted to see the page curve finally emerging from a gravity calculation, vindication that quantum mechanics prevailed even in the most extreme environments. What is certain is that the result was a milestone, a breakthrough that had been decades in the making, drawing on contributions from hundreds of physicists over nearly half a century. The lonely paradox that Hawking had posed in 1974 had catalysed an extraordinary program of research, forcing physicists to confront questions about the nature of information, the emergence of space-time, and the fundamental principles governing the universe. Now, at last, there was a calculation that brought these threads together, that showed how information could be preserved even as black holes evaporated, that reconciled the demands of quantum mechanics with the geometry of general relativity in a new and unexpected way. The calculation existed. The formula worked. The page curve emerged from the mathematics with an elegance that surprised even its architects. But in the months following those initial papers in 2019, as the results spread through the theoretical physics community like a slow-burning fire, a deeper unease began to surface. The island formula answered one question only to raise a dozen more, each more vertiginous than the last. What did it mean that regions of space-time could suddenly belong to a distant observer's entanglement wedge? What was happening to locality, that bedrock assumption that physics occurs at points and propagates through space? And perhaps most troubling of all, what did the island formula imply about the nature of space-time itself? These were not merely technical puzzles to be worked out in follow-up papers. They were conceptual earthquakes, tremors that threatened to reshape the entire landscape of theoretical physics. The community that had celebrated the derivation of the page curve now found itself grappling with implications that went far beyond black holes, implications that touched on the deepest questions about reality that physics could pose. The trouble began with a simple observation about the island formula itself. When you calculated the generalized entropy according to the prescription, when you found the quantum extremal surface that minimized the total entropy, something strange happened at late times in black hole evaporation. The island, that region inside the black hole that contributed to the radiation's entropy, grew. It encompassed more and more of the black hole interior as the evaporation proceeded. By the time the black hole was near the end of its life, the island had swallowed almost everything behind the horizon. The interior of the black hole, in a very precise sense, had become part of the radiation. This was not metaphor. It was not poetic license or a convenient way of speaking. The mathematics said, quite explicitly, that the quantum information in the island region was encoded in the Hawking radiation outside the black hole. An observer collecting radiation at infinity could, in principle, reconstruct what was happening inside the black hole. The interior was, in the language of quantum information, redundantly encoded in the exterior. For physicists accustomed to thinking of the black hole interior as fundamentally separated from the outside universe, this was deeply counterintuitive. The event horizon was supposed to be a one-way membrane, a point of no return. Once you crossed it, you were committed to falling toward the singularity. No signal, no influence, no information could escape. This was what the horizon meant, what it had always meant since Schwarzschild first wrote down his solution in 1916. And yet here was a calculation suggesting that the interior was somehow accessible from the outside, that the rigid separation enforced by the horizon was less absolute than it appeared. The resolution of this apparent contradiction lay in a subtle distinction that would become central to all subsequent discussions. The island formula did not say that an observer could send a probe into the black hole and retrieve information. It did not violate the classical expectation that nothing escapes from behind the horizon. What it said instead was that the quantum state of the interior was not independent of the quantum state of the radiation. They were entangled in a very specific way, entangled such that complete knowledge of the radiation would allow you to reconstruct the interior without ever going inside. This was a profound shift in perspective. It suggested that the black hole interior was not a separate region of space-time in the ordinary sense, but rather an encoded description that could be read from the outside if you knew how. The geometry of space, the smooth manifold that physicists had learned to work with since Einstein, was not fundamental. It was emergent, arising from patterns of quantum entanglement that could be sliced and reorganized in ways that defied naive spatial intuition. Physicists began speaking of space-time as an entanglement structure, a network of correlations that gave rise to the appearance of geometric space. In this picture, the island formula was not discovering new regions of space-time. It was revealing that the entanglement structure had a different connectivity than the geometric picture suggested. The radiation and the island were connected by quantum entanglement, even though geometrically they were on opposite sides of a horizon. The quantum description was more fundamental than the spatial one. This idea was not entirely new. It had been implicit in the ADS-CFD correspondence since its inception. The duality said that a gravitational theory in the bulk was equivalent to a non-gravitational theory on the boundary, a theory with no spatial dimensions corresponding to the bulk radial direction. Space itself in this correspondence emerged from boundary physics. The entanglement structure of the boundary theory determined the geometry of the bulk. This connection had been made explicit in 2006 by the Japanese physicists Shinsei Ryu and Tadashi Takayanagi, who showed that the entanglement entropy of a region in the boundary theory was proportional to the area of a minimal surface in the bulk. The Ryu-Takayanagi formula connected quantum information to geometry in a precise, calculable way. The island formula was, in a sense, a generalization of this insight, extending it to dynamical situations where gravity was important. But the island formula pushed this connection further than it had ever gone before. It showed that the entanglement structure could be so complex that it included regions behind horizons, regions that were geometrically inaccessible but quantumly connected. The implications rippled outward from black holes to cosmology, from the early universe to the far future, from the nature of measurement to the meaning of reality itself. Consider what the island formula implied about the experience of an observer falling into a black hole. In the classical picture, such an observer would cross the horizon smoothly, noticing nothing special at the moment of transition. The equivalence principle, Einstein's foundational insight, guaranteed that local physics at the horizon would be indistinguishable from physics anywhere else. The observer would continue falling, experiencing increasingly strong tidal forces as they approached the singularity, but the horizon crossing itself would be uneventful. This picture had been challenged before, most dramatically by the firewall proposal of Almieri, Marolf, Polchinski and Sully in 2012. They had argued that if information was truly preserved, if the Hawking radiation was pure rather than thermal, then quantum mechanics seemed to demand that the horizon become a violent, energetic barrier, a firewall that would incinerate any observer who tried to cross. This was a disturbing conclusion, one that violated the equivalence principle, and suggested that black holes were far stranger than anyone had imagined. The island formula offered a different perspective. In the island picture, the horizon did not need to become a firewall. The observer could fall through smoothly, just as Einstein's equation suggested. But the interior they experienced, the geometry of space they traversed on their way to the singularity, was encoded in the radiation outside. There was a single quantum state describing both the interior experience and the exterior radiation, and that state preserved information. The apparent paradox dissolved not through violence at the horizon, but through a reconceptualization of what the interior meant. This resolution was elegant, but it raised its own puzzles. If the interior was encoded in the radiation, if two different physical systems, the geometric black hole interior and the collection of Hawking particles, described the same quantum information, then what was real? Was there truly a geometric space inside the black hole, a region that an infalling observer would experience? Or was that experience itself a kind of emergent phenomenon, a story told by patterns of entanglement that had no independent existence? Different physicists interpreted the mathematics differently. Some held firmly to a view in which the interior geometry was real, in which an observer falling through the horizon would have genuine experiences that mattered. The encoding in the radiation was a consequence of quantum mechanics, a reflection of how information could be distributed across multiple systems, but it did not diminish the reality of the interior. Others took a more radical position, suggesting that the interior only existed from the perspective of an infalling observer, that there was no observer-independent fact about what happened behind the horizon. The radiation's description and the interior description were complementary, different ways of looking at the same underlying quantum reality, neither more fundamental than the other. This disagreement about interpretation might seem like philosophy, a question about how to talk, rather than a question about physics. But it had concrete implications that physicists were struggling to work out. If the interior was truly encoded in the radiation, then operations performed on the radiation should, in principle, affect the interior. This was the essence of the ER-EPR proposal that Maldacena and Susskind had advanced in 2013, the idea that entanglement and geometric connection were two aspects of the same phenomenon. But what kinds of operations? What effects? And could this encoding ever lead to contradictions, situations where the interior and exterior descriptions made incompatible predictions? These questions were being investigated in a flurry of papers throughout 2020 and 2021, as physicists pushed the island formula into new regimes and tested its limits. One particularly fruitful direction involved double holographic models, setups in which a gravitational theory was itself dual to another gravitational theory, which was in turn dual to a non-gravitational boundary theory. These nested dualities allowed physicists to track the same physical situation through multiple descriptions, checking for consistency and looking for new insights. The results were reassuring in some ways, troubling in others. The different descriptions did seem to be consistent, at least in the regimes where calculations were tractable. The island formula gave the same answer whether you computed in the bulk or on the boundary, whether you used one description or another. This was evidence that the formula was capturing something real, something about the fundamental structure of quantum gravity that transcended any particular calculational scheme. But the calculations also revealed how little physicists understood about the mechanisms underlying these results. The island formula told you what to compute, but it did not explain why that prescription worked. It was like being handed a recipe without understanding the chemistry behind it. You could follow the steps and get the right answer, but the deeper question, why these steps, why this answer, remained obscure. The search for understanding led physicists back to the replica trick, the mathematical technique that had been used to derive the island formula in the first place. In that derivation, you imagine making multiple copies of your system, computing certain quantities in the replicated system, and then analytically continuing to find the entropy. This procedure, while mathematically justified in specific cases, had a somewhat magical quality. Where did the replicas come from? What did they mean physically? Why did the analytic continuation give sensible answers? Attempts to answer these questions led to a deeper investigation of the path integral, the fundamental calculational tool of quantum theory. In quantum mechanics and quantum field theory, the path integral sums over all possible histories of a system, weighting each history by a phase factor determined by its action. This sum, which is really an infinite dimensional integral over the space of all possible field configurations, encodes the quantum evolution of the system. It was introduced by Richard Feynman in the 1940s and had become the lingua franca of theoretical physics. In quantum gravity, the path integral takes on a new character. You're not summing over field configurations on a fixed background space-time. You're summing over geometries themselves, over all possible shapes that space-time could take. This gravitational path integral is fiendishly difficult to define rigorously. The space of geometries is infinite dimensional, the integral is not obviously convergent, and the very notion of all possible geometries is problematic. Nevertheless, physicists had developed techniques for extracting sensible answers in certain limits, particularly in the semi-classical regime where the geometry is close to a classical solution. The derivation of the island formula relied on a specific property of the gravitational path integral. When you applied the replica trick, when you computed the entropy of the radiation by considering multiple copies of the system, you found that the path integral included contributions from geometries that connected the replicas in unexpected ways. These were not the obvious geometries where each replica was independent. They were geometries where the replicas were sewn together through space-time wormholes, tiny tunnels in the fabric of space-time that linked one copy to another. These replica wormholes were the key to everything. Without them, the calculation would give Hawking's answer, the steadily rising entropy that violated unitarity. With them, the calculation gave the page curve, the entropy that rose and then fell, preserving information and satisfying quantum mechanics. The replica wormholes were not optional decorations. They were necessary contributions that had been overlooked in all previous calculations. Their inclusion changed the answer and resolved the paradox. But what were these wormholes, exactly? In the replica trick calculation, they appeared as mathematical constructs, geometries that contributed to a formal integral. But did they have physical reality? Were there actually wormholes connecting different copies of the universe? Or was this just a calculational artifact, a convenient trick for getting the right answer? The question was not easy to resolve. The replica trick involved taking a limit in which the number of replicas approached 1, a limit that was not straightforward to interpret physically. You were computing entropy in a single system by considering multiple copies and then extrapolating, a procedure that seemed to attribute physical significance to something that was purely imaginary. And yet the answer it gave was physically correct, at least as far as anyone could tell. The entropy did follow the page curve. Information was preserved. Whatever the replicas meant, they were telling the truth. Some physicists argued that the replica wormholes should be understood as contributions from other universes, from copies of our reality that existed in some fundamental sense and contributed to our physics. This interpretation was radical, but not without precedent. The idea of a multiverse, a vast collection of parallel universes with different properties, had been floating around theoretical physics for decades. Replica wormholes might be giving us a glimpse of this multiverse, showing that our universe was not isolated but connected to others through quantum gravitational effects. Others were more cautious, suggesting that the replica wormholes were best understood as encoding certain statistical properties of quantum gravity rather than as literal geometric connections. In this view, the path integral over geometries was not a sum over actual spacetimes that existed, but rather a calculational device for capturing the behaviour of a single, highly complex quantum system. The wormholes were bookkeeping tools, not physical entities. This debate about the reality of spacetime wormholes, about the meaning of the gravitational path integral, about the interpretation of the replica trick, continues to this day. It is not merely a philosophical dispute. Different interpretations lead to different predictions about situations beyond the ones that have been calculated. If replica wormholes are real, if they connect different branches of a multiverse, then there should be other physical effects arising from this connection. If they are merely computational devices, then the physics might be different. Resolving these questions will require either new calculations, probing regimes where the different interpretations make different predictions, or new conceptual frameworks that clarify what the mathematics is really saying. As the community grappled with these interpretational challenges, the practical work continued. New models were constructed, testing the island formula in different settings. Extensions were proposed, generalizing the formula to situations beyond the evaporating black hole. Applications were explored, connecting the insights from black hole physics to other areas of quantum gravity research. One particularly active area involved the study of baby universes, small, self-contained regions of spacetime that branched off from our universe and developed independently. Baby universes had been studied sporadically since the 1980s, when Stephen Hawking and others had proposed that they might appear in quantum gravity, but the island formula gave these speculations new life. The replica wormholes that appeared in the entropy calculation could be interpreted as connections to baby universes, new regions of spacetime that were quantum mechanically entangled with our own. If baby universes existed, they could have profound effects on physics. They would introduce new sources of randomness, new uncertainties that went beyond the familiar quantum mechanical probabilities. They might explain why certain quantities in physics, like the cosmological constant, had values that seemed arbitrary, values that could only be predicted statistically rather than deterministically. The island formula, and the replica wormholes it revealed, might be telling us that our universe was not self-contained, that its physics was influenced by a vast ensemble of other universes that we could never directly observe. These ideas were speculative, going well beyond what the calculations could rigorously support. But they illustrated the range of possibilities that the island formula opened up. A technique developed to compute the entropy of Hawking radiation had led to insights about the nature of space-time, the meaning of the gravitational path integral, the existence of wormholes and baby universes, and the possibility of a multiverse. The original paradox, what happens to information when matter falls into a black hole, had become a gateway to the deepest questions in physics. By 2021, the island formula had established itself as a central tool in quantum gravity research. Papers citing the original works numbered in the hundreds. Conferences devoted sessions to discussing and extending the results. Graduate students entering the field were learning the island formula as part of their standard training, alongside the classic results of Hawking and Bekenstein. A new generation of physicists was being shaped by these ideas, by a perspective in which space-time was emergent, information was fundamental, and the boundaries between regions could be reshuffled by the demands of quantum mechanics. But success brought its own challenges. As the island formula became mainstream, as it was applied to ever more exotic situations, the limitations of the approach became clearer. The formula had been derived and tested primarily in the context of ADS-CFT, in the artificial setting of anti-de Sitter spacetime with its special properties. Our actual universe was different. It was not anti-de Sitter, but de Sitter, an expanding spacetime with a positive cosmological constant. It did not have a boundary at spatial infinity where a dual theory could live. The techniques that worked so beautifully in the theoretical sandbox might not apply to the universe we actually inhabited. This was not a new concern. Throughout the history of quantum gravity, physicists had worried about the applicability of their results beyond the special cases where calculations were possible. But the island formula sharpened the concern. Here was a result that seemed to resolve a decades-old paradox, that seemed to tell us something fundamental about how information behaved in the presence of black holes. If this result only applied to certain kinds of universes, if it failed in our own, then what had really been achieved? The attempt to extend the island formula to de Sitter space became one of the major research programs of the early 2020s. The technical difficulties were formidable. De Sitter space had horizons of its own, cosmological horizons that separated observers from regions they could never see. These horizons were different from black hole horizons in important ways. They were observer-dependent, for one thing, present for some observers and absent for others. Applying the island formula in this context required new ideas, new techniques, and a willingness to venture beyond the established mathematical frameworks. Some progress was made. Papers appeared proposing island formulas for cosmological spacetimes, suggesting that the same basic insights might apply in de Sitter as in anti-de Sitter. But the results were preliminary, the calculations less robust than in the black hole case. The jury was still out on whether the island formula represented a universal truth about quantum gravity or a special feature of certain tractable examples. And beneath all the technical questions, the conceptual challenge remained. The island formula assumed that spacetime was a meaningful backdrop on which calculations could be performed, that there was a geometry in which islands and horizons and entanglement wedges made sense. But the deepest approaches to quantum gravity, string theory, loop quantum gravity, causal set theory, and others, suggested that spacetime itself was emergent, that it dissolved into something more fundamental at the smallest scales. How did the island formula fit with these ideas? Was it a glimpse of the fundamental theory, or merely a useful approximation valid in certain regimes? These questions were being asked in seminar rooms and conference halls around the world. They were debated in late-night discussions among graduate students and in careful correspondence among senior researchers. The island formula had not answered everything. It had, in a sense, raised the stakes, showing that progress was possible, but leaving the ultimate answers tantalizingly out of reach. The questions multiplied even as the answers accumulated, and perhaps no question pressed more urgently than the one that had lurked beneath the surface of the entire enterprise, the question that separated genuine resolution from mere mathematical sleight of hand. The island formula calculated entropies, traced page curves, showed that information could be recovered in principle, but it said nothing about how. It said nothing about the mechanism by which the information encoded in a collapsing star, in the quantum correlations of infalling matter, actually made its way back out of the black hole and into the Hawking radiation. The formula told you that the radiation's entropy decreased at late times, that correlations built up, that unitarity was preserved. But the radiation itself, emerging from the vacuum fluctuations near the horizon, seemed to know nothing of what had fallen in. The photons and electrons streaming away from an evaporating black hole did not carry obvious imprints of the star's original composition, of whether it had been made of hydrogen or helium, of whether it had harboured planets, or simply drifted alone through empty space. The information was there, the island formula guaranteed it, but how it got there remained mysterious. This was the question of the mechanism, and it would consume theorists for years. The island formula had identified the islands, had shown that they contributed to the entropy calculation. But the islands were inside the black hole behind the event horizon. The Hawking radiation was outside, streaming toward infinity. How did the information cross from one region to the other? What physical process carried it across the horizon and imprinted it on the outgoing modes? One possibility, explored by Pennington and others, was that the answer lay in the subtle correlations between the early and late Hawking radiation. In the standard semi-classical picture, each photon emitted from the black hole was produced independently, without correlation to what had come before. But the island formula suggested this picture was incomplete. At the Page time, when the islands first appeared, the radiation's entanglement structure underwent a dramatic transition. Perhaps this transition corresponded to the emergence of correlations, to patterns in the radiation that encoded information about the black hole's interior. The information would not be carried by individual photons, but by the relationships between them, by the subtle quantum correlations that only revealed themselves when you looked at the radiation as a whole. This was reminiscent of ideas that had been floating around for decades, suggestions that information emerged through subtle corrections to the Hawking calculation, through tiny deviations from perfect thermal behaviour that accumulated over the black hole's lifetime. The island formula gave these ideas a concrete mathematical form. It said that the corrections were real, that they had a definite magnitude, that they grew with time until they became the dominant effect. But it still did not say what the corrections were, what physical mechanism produced them. Another approach focused on the replica wormholes themselves. In the path integral calculation, the wormholes connected different copies of space-time, allowing information to flow between them. Perhaps this was more than a mathematical trick. Perhaps the wormholes were real in some sense, and information really did flow through them. This idea led to speculations about the nature of space-time, about whether the smooth geometry we observed was merely an approximation to a more complicated quantum reality, in which distant regions could be connected in unexpected ways. The connection to EREPR became crucial here. If entanglement and geometry were two faces of the same phenomenon, then the correlations in the Hawking radiation might literally be wormholes, microscopic connections threading through the fabric of space-time and linking the radiation to the black hole interior. The information would flow through these connections, carried by the quantum correlations themselves. The island formula would then be telling us something about the topology of space-time, about the hidden connections that made information transfer possible. These ideas were beautiful but speculative. They pushed beyond what the calculations could rigorously establish. The island formula was a tool for computing entropies, not for tracing the paths of individual bits of information. It told you the answer without showing you the work. This was both a strength and a limitation. It meant the formula could be applied even when the detailed dynamics were too complex to follow. But it also meant that the deepest questions, the questions of how, remained partially unanswered. The search for mechanism led researchers back to older ideas, to the black hole complementarity of Susskind and the fuzzball proposal of Samir Mathur. Perhaps the island formula was compatible with these pictures, perhaps it even required them. If the black hole interior was somehow encoded in the exterior, if the horizon was not a smooth surface but a complicated quantum state, then the islands might be manifestations of this encoding. The interior would not be truly inside. It would be distributed, smeared across the radiation in ways that only became apparent when you asked the right questions. Mathur's fuzzballs had been controversial since their introduction in the early 2000s. The idea was that black holes in string theory were not empty voids with singularities at their centres, but rather highly excited string states, quantum objects with no interior in the conventional sense. The fuzzball would have the same mass and charge as a black hole, would look like a black hole from far away, but up close it would be something entirely different, a ball of strings and brains with a surface rather than a horizon. The island formula gave fuzzballs new life. If the interior was not really interior, if it was somehow part of the exterior in the entanglement sense, then perhaps the fuzzball picture was correct. Perhaps the islands were telling us that the naive geometric picture of a black hole, with its smooth horizon and empty interior, was simply wrong. The information was not lost because there was no interior for it to be lost in. This was radical, and not everyone accepted it. Many physicists remained committed to the idea that black holes had conventional interiors, that an observer falling through the horizon would experience nothing special, that the firewall paradox was resolved by some subtlety rather than by the elimination of the interior itself. The island formula was agnostic on this point. It computed entropies without committing to a particular picture of the black hole's internal structure. Different researchers interpreted the same calculations in different ways, projecting their theoretical prejudices onto the mathematical framework. The debates played out in papers and seminars, in comment sections and email exchanges. They revealed the limits of what had been achieved. The page curve was now under control, the entropy calculations agreed with unitarity, but the picture of a black hole as a physical object, as something you could fall into and explore, remained contested. The island formula was a map, but the territory it described was still being surveyed. Meanwhile, the mathematical machinery continued to develop. The derivation of the replica wormholes had relied on specific features of the path integral, on the sum over geometries that characterized quantum gravity. But path integrals were notoriously difficult to define rigorously, especially in gravitational theories. The sum over all possible spacetime geometries included geometries that were singular, geometries that were topologically complicated, geometries that defied standard mathematical analysis. Making sense of this sum, extracting reliable predictions from it, was one of the great unsolved problems of theoretical physics. The replica wormholes highlighted these difficulties. The wormhole contributions were found by saddle point approximation, by looking for the geometries that extremised the gravitational action. But how did you know you had found all the saddle points? How did you know there were not other contributions, other geometries that would change the answer? The calculations worked because they gave sensible results, because they reproduced the page curve, but this was a somewhat circular argument. The theoretical foundations were shaky, even as the phenomenological success was undeniable. Some researchers tried to put the calculations on firmer footing. They studied simplified models, toy universes where the path integral could be defined more carefully. They developed new mathematical techniques for handling the sum over geometries. They looked for alternative derivations that did not rely so heavily on saddle point approximations. Progress was made, but slowly. The foundations of quantum gravity remained obscure, the path integral remained mysterious, and the island formula floated somewhat unmoored, a powerful tool whose ultimate justification was still being sought. The situation was reminiscent of earlier episodes in physics. Quantum electrodynamics, the theory of electrons and photons, had been plagued by infinities in the 1930s and 1940s. Calculations gave absurd, infinite answers that could not be physical. The renormalization program developed by Tomonaga, Schwinger, Feynman and Dyson provided a recipe for extracting finite predictions from the theory. The recipe worked spectacularly well, making QED the most accurately tested theory in physics. But for decades, the recipe remained somewhat mysterious, a trick that gave the right answers without a deep justification. Only later, with the development of the renormalization group and effective field theory, did a clearer picture emerge of why the trick worked. Perhaps the island formula was in a similar position. Perhaps it was giving correct answers without yet being fully understood. Perhaps the foundations would come later, when the deeper theory was better developed. For now, physicists were content to use the tool, to apply it to new situations, to see what it could teach them. The pragmatic approach had served physics well in the past, and the applications continued to multiply. One of the most striking was to the question of entanglement islands in flat space-time. The original derivations had relied heavily on the properties of anti-de Sitter space, on the existence of a boundary and a dual theory. But our universe was not anti-de Sitter, and any claims to have resolved the information paradox would ultimately have to apply to flat or de Sitter space-time. Could islands appear in these more realistic settings? The answer, it turned out, was yes, at least in certain circumstances. Papers in 2020 and 2021 showed that entanglement islands could form in flat space-time, provided the setup was arranged correctly. The key was to have a system that could absorb the Hawking radiation, a kind of reservoir that collected the emitted particles and allowed their entanglement to be computed. With such a reservoir in place, the island formula could be applied, and islands appeared. These results were both encouraging and troubling. Encouraging because they showed the island phenomenon was not confined to special spacetimes. Troubling because they required the artificial introduction of a reservoir, an absorbing system that did not exist in the original formulation of the black hole evaporation problem. Hawking had imagined a black hole in isolation, radiating into empty space. The island calculations worked best when the radiation was collected by some external system. This raised questions about the physical interpretation. Was the island formula telling us something about black holes themselves, or about the particular way we chose to observe and measure their radiation? The debates on this point were technical but consequential. Some argued that the reservoir was essential, that information recovery required an absorbing system to disentangle the radiation from the quantum state of the horizon. Others maintained that the reservoir was a mathematical convenience, that the islands were real regardless of whether anyone collected the radiation. The truth probably lay somewhere in between, but pinning it down required clearer understanding of the measurement process in quantum gravity, of how observers and observations fit into the framework. The difficulties were compounded when researchers turned to de Sitter space, to universes like our own. De Sitter space posed unique challenges. Every observer was surrounded by a cosmological horizon, a surface beyond which light could never reach them. This horizon was not a property of any physical object like a black hole, but a consequence of the expansion of space itself. The horizon was observer-dependent, different for different observers in different places. Did de Sitter space have its own information paradox? Could the cosmological horizon emit radiation analogous to Hawking radiation? These questions had been asked since the 1970s, when Gibbons and Hawking first computed the temperature of the cosmological horizon. But the answers remained elusive. De Sitter space was not a black hole. It did not form from collapse and evaporate away. It was eternal, or at least extremely long-lived, persisting as long as the cosmological constant remained positive. What did information loss even mean in such a context? The island formula offered a way to approach these questions, but the results were confusing. Papers proposed various generalizations, various ways to apply the entropy calculations to cosmological horizons, but the physical interpretation was unclear. Did the cosmological horizon have interior degrees of freedom? Was there a cosmic analogue of the island, a region behind the cosmological horizon that contributed to the entropy of our observable universe? If so, what did this mean for our understanding of cosmic history, of the evolution of the universe from the Big Bang to the present day? These questions verged on cosmology, on the nature of the early universe and the fate of the late universe. They connected the island formula to some of the deepest problems in physics: the origin of the arrow of time, the nature of the cosmic microwave background, the problem of initial conditions. The island formula, born from the specific technical problem of black hole evaporation, was beginning to reach far beyond its origins. The reach was exhilarating, but also dangerous. Theoretical physics has a history of overreach, of ideas that seem universal but turn out to be parochial, valid only in the special cases where they were first discovered. The island formula might be such a case. It might be telling us profound truths about quantum gravity, or it might be an artifact of the special setups where reliable calculations were possible. Distinguishing between these possibilities required more work, more calculations, more conceptual clarity. The community was divided. Some researchers were triumphant, declaring the information paradox solved and moving on to new problems. Others were skeptical, pointing to the gaps and limitations, the questions that remained open. The majority occupied a middle ground, acknowledging the progress while recognizing the incompleteness. This was the normal process of science, the messy reality behind the clean narratives of discovery. Ideas emerged, were tested, were refined, were sometimes abandoned. The island formula was in the testing phase, being pushed and probed to see what it could and could not explain. One particularly fertile ground for testing was the study of wormholes. Not the replica wormholes of the entropy calculation, but potentially traversable wormholes, connections between distant regions of space-time that might allow passage. The ER-EPR conjecture had already linked entanglement to wormholes. The island formula, with its reliance on non-trivial topology, seemed to support this connection. Papers explored whether the islands themselves could be interpreted as wormhole mouths, whether the information that emerged in the Hawking radiation had literally travelled through a wormhole from the black hole interior. These were speculative ideas, not yet backed by rigorous calculation. But they captured the imagination. Wormholes had long been a staple of science fiction, portals to distant stars or parallel universes. If the island formula was telling us that wormholes were not just fictional devices, but essential features of quantum gravity, that information really did flow through tunnels in space-time, then the implications were staggering. The boundary between science and speculation became blurred, and researchers had to be careful to distinguish what had been proven from what had been imagined. The year 2022 saw a consolidation of the field. The flurry of papers had begun to settle into a consensus, at least on the technical results. The island formula worked. It reproduced the page curve. It was consistent with unitarity. The replica wormholes provided a derivation within the path integral formalism. These results were accepted by most workers in the field, incorporated into the standard toolkit of quantum gravity research. But the deeper questions remained open. What was the fundamental theory that underlay the island formula? Was space-time emergent, and if so, from what? How did information actually escape the black hole? Through what physical process? What happened to an observer who fell into a black hole? Did they encounter a firewall, a smooth horizon, a fuzzball, or something else entirely? The island formula constrained the answers but did not determine them. Multiple pictures remained consistent with the mathematical results, and choosing among them required input that the calculations alone could not provide. The philosophical implications were also being digested. If the island formula was correct, if information was preserved in black hole evaporation, then quantum mechanics was safe. The unitarity that underlay all of quantum theory was not violated by gravitational collapse. This was a relief, but it also raised new puzzles. Quantum mechanics and general relativity remained in tension, even if they no longer directly contradicted each other. The smooth space-time of Einstein's theory seemed to be an approximation to something stranger, a quantum geometry in which regions could be connected or disconnected depending on the questions you asked. The implications for our understanding of reality, of what exists and how things are connected, were only beginning to be explored. In the years following the initial breakthroughs, the island formula became a lens through which physicists examined a wide range of problems. It was applied to cosmological spacetimes, to holographic theories, to models of quantum error correction and quantum computing. Each application revealed new facets of the idea, new connections to other areas of physics and mathematics. The formula was not just a solution to a single paradox, but a window into the structure of quantum gravity itself. And through it all, the figure of Stephen Hawking loomed. He had posed the paradox half a century earlier. He had defended information loss for decades, only to concede in 2004 that information was probably preserved. He had not lived to see the island formula, had not seen the page curve calculated from first principles. But his work was the foundation on which everything rested. Without his discovery of Hawking radiation, there would have been no paradox to resolve. Without his insistence on taking the paradox seriously, generations of physicists would not have been driven to find an answer. The resolution, when it came, was a vindication of the questions he had asked, even if it contradicted the answers he had long believed. The legacy was complex. Hawking had been wrong about information loss, but he had been right to demand an answer. He had been wrong about black holes destroying information, but he had been right that black hole evaporation posed a fundamental challenge to physics. His willingness to confront the paradox, to insist that it mattered, had shaped the field for generations. The physicists who finally resolved the paradox stood on his shoulders, even as they overturned his conclusions. The victory was not announced with fanfare. There was no press conference, no moment of collective celebration broadcast to the world. Physics does not work that way, not usually. Instead, the triumph arrived quietly, distributed across hundreds of papers and thousands of conversations, absorbed into the bloodstream of a discipline that had grappled with a single question for nearly 50 years. By the close of 2022, the community had reached something approaching consensus, a rare and precious commodity in theoretical physics. Information is not destroyed in black holes. Unitarity survives. Quantum mechanics, the bedrock theory that had predicted every experiment ever devised to test it, remained inviolate even in the most extreme gravitational environments the universe could produce. The implications of this resolution extended far beyond the immediate problem. For decades, the information paradox had served as a fault line, a crack in the foundations that threatened to widen with every new analysis. Physicists had nightmares, quite literally, about what it would mean if information were truly destroyed. The entire edifice of modern physics, quantum field theory, the Standard Model, our understanding of atoms and light and matter, rested on the assumption that evolution was unitary, that the laws governing the present contained complete information about the past. Violation of unitarity would not just be a curiosity confined to black holes, it would be a catastrophe, a signal that the universe operated according to rules fundamentally different from those we had painstakingly discovered. It would mean that probability itself could leak away, that the careful bookkeeping of quantum mechanics was an illusion, that at the deepest level, information simply vanished from reality. This possibility had haunted the field since 1976, and now, at last, it had been exercised. The resolution came not as a single discovery, but as a convergence of insights, a tide that lifted all boats simultaneously. The island formula, the page curve calculations, the replica wormholes, the connections to holography and AIRD-S-CFT. These were not separate achievements but facets of a single crystalline structure that had finally come into focus. The picture that emerged was strange, counterintuitive, almost alien in its implications. Space-time was not fundamental. The smooth geometry of Einstein's relativity, the curved manifolds on which stars and planets and black holes existed, was itself an emergent phenomenon, arising from something more primitive, more quantum mechanical in character. This idea had been circulating for decades, implicit in string theory and explicit in holographic dualities. But the island formula made it concrete in a way previous arguments had not. The very concept of locality, the assumption that events separated by distance are independent, that what happens here does not instantly affect what happens there, became suspect. Islands demonstrated that in quantum gravity, regions of space-time could be entangled in ways that defied naive geometric intuition. A piece of the black hole interior, deep behind the horizon, could be encoded in the radiation streaming away to infinity. The two regions, seemingly disconnected by the causal structure of space-time, were quantum mechanically identical, two descriptions of the same underlying reality. This was not just a technical statement about Hilbert spaces and density matrices. It was a revision of our fundamental ontology, our picture of what the universe is made of and how its parts relate. For 3 centuries, physics had proceeded on the assumption that the world was composed of distinct objects located at distinct places, interacting through forces that propagated at finite speeds. Quantum mechanics had already challenged this picture, introducing entanglement and non-local correlations that seemed to stretch across space instantaneously. But gravity had always been the last bastion of classical intuition, the arena where space-time itself provided the stage on which the quantum drama unfolded. Now, the island formula suggested that space-time itself was woven from entanglement, that the geometric relationships we perceived were emergent phenomena arising from deeper quantum correlations. The boundary between what was inside the black hole and what was outside was not absolute, but dependent on the questions being asked, the measurements being performed. Reality, at its most fundamental level, was not a collection of localized events arranged on a spatial canvas. It was something richer, stranger, more interconnected than anything Newton or Einstein had imagined. The physicists who had driven this revolution knew they were not finished. The island formula was a tool, not a theory. It told them what the answer was without fully explaining how or why. It constrained the possibilities without selecting among them. In the immediate aftermath of the breakthroughs, multiple competing pictures remained consistent with the mathematical results. Perhaps information escaped through subtle quantum correlations in the radiation, too delicate to detect without measuring every Hawking photon with impossible precision. Perhaps the horizon was not quite where classical theory predicted, the geometry slightly modified by quantum effects in ways that allowed information to leak out. Perhaps the black hole interior was an illusion, a description valid from certain perspectives but not from others, the true reality residing in a lower dimensional holographic encoding on the boundary. Perhaps none of these pictures was quite right, and the true explanation lay in some deeper framework not yet discovered. The island formula was compatible with all of these possibilities and distinguished between none of them. This incompleteness was not a failure, but a mark of honest science. The formula had done what decades of speculation had not. It had provided a concrete, calculable result that agreed with the predictions of unitarity. It had demonstrated that the information paradox could be resolved within the framework of semi-classical gravity, augmented by quantum extremal surfaces, without requiring exotic new physics or radical departures from established principles. This was an enormous achievement, the kind of breakthrough that happens perhaps once in a generation. But it was also an invitation to go deeper, to understand the mechanisms behind the formula, to construct the fundamental theory that would explain why islands existed and how information actually made its way from the black hole interior to the external universe. The search for this deeper theory consumed the years that followed. New workshops and conferences were organised, dedicated to the quantum information aspects of gravity, to the nature of space-time emergence, to the connections between islands and other phenomena like cosmological horizons and traversable wormholes. Graduate students who had never known a time when the information paradox was unsolved began their careers working on these extensions, pushing the ideas into new domains, testing their limits and implications. The field had been transformed, the paradigm shifted, and everyone was working to understand what the new landscape looked like. One of the most profound realizations to emerge from this period concerned the role of observers. In classical general relativity, observers are passive witnesses to the geometry of space-time. They move along geodesics, experience time dilation and gravitational redshift, fall through horizons or orbit outside them, but they do not, by their presence or measurements, alter the fundamental structure of space and time. Quantum mechanics changes this picture in subtle ways. Measurement plays a constitutive role. The act of observation is not separate from the phenomenon observed. The island formula extended this quantum insight to gravity itself. The location of the island, the boundary of the entanglement wedge, depended on what was being computed, what region's entropy was being evaluated, what information was being sought. Different questions yielded different answers about which portions of space-time were accessible to which observers. The universe, it seemed, did not come pre-divided into inside and outside, accessible and inaccessible. These distinctions were imposed by the questions asked of it. This had startling implications for the experience of observers falling into black holes. The island formula preserved information as seen from outside, ensuring that the radiation carried away everything that had ever fallen in. But what did this mean for an observer crossing the horizon? The classical picture, cherished since the 1960s, held that nothing special happened at the horizon, that an infalling observer experienced only smooth space-time until they were destroyed by tidal forces near the singularity. But if information was somehow being transferred to the radiation, some process had to be responsible. The firewall argument had suggested that this process might be violent, that the horizon was replaced by a wall of high-energy particles that would incinerate anything that touched it. But the island formula did not require firewalls. Indeed, many of its practitioners believed that firewalls were unnecessary, that information could escape through more subtle mechanisms that left the infalling experience smooth. The debate was not resolved, and perhaps could not be resolved, without more information about the microscopic theory of quantum gravity. But the island formula had changed the terms of the argument. Before, it had been possible to doubt whether information was preserved at all. Now, that doubt had been largely dispelled. The question was no longer whether unitarity held, but how it held, through what physical processes the bookkeeping of quantum mechanics was maintained in the presence of gravitational collapse. This was still a profound question, still the subject of intense research and speculation. But it was a different kind of question than the one Hawking had posed in 1976. It was a question that assumed the answer to the paradox and sought to understand the mechanisms behind that answer. The year 2023 brought further developments, as the ideas continued to mature and spread. The island formula was applied to situations beyond simple black holes. Cosmologists began exploring its implications for the early universe, for de Sitter space, for the quantum state of the cosmos as a whole. If space-time was emergent, if entanglement was the glue holding geometry together, then perhaps these insights could shed light on the biggest questions of all: how the universe began, whether anything came before the Big Bang, what the ultimate fate of cosmic expansion might be. The tools developed to solve the information paradox were repurposed for cosmological questions, and new connections were forged between quantum gravity and observational cosmology. It remained to be seen whether these connections would yield testable predictions, whether the ideas born from black hole physics could ever touch the data collected by telescopes and detectors. But the possibility was tantalizing, a dream of unity between the smallest scales of quantum mechanics and the larger scales of cosmological structure. Through all of this, the human element remained. Science is not conducted by abstract intellects operating in a vacuum. It is conducted by people, driven, flawed, brilliant, stubborn, generous, competitive people, working together and against each other in the pursuit of understanding. The resolution of the information paradox was no different. It bore the fingerprints of the individuals who had fought for it, who had dedicated their careers to a problem that seemed at times impossibly difficult, who had risked their reputations on ideas that their colleagues sometimes dismissed as too speculative or too mathematical. Ahmed al-Hayri, whose firewall paper had reopened the paradox and whose island paper had helped close it. Netta Engelhardt and Jeff Pennington, whose quantum extremal surface formula had provided the crucial insight. Akers, Stanford, Saad, Schenker, and the dozens of others who had contributed essential pieces to the puzzle. Juan Maldacena, whose ADCFT correspondence had laid the groundwork 2 decades earlier. Leonard Susskind, who had championed information preservation when much of the community was sceptical. John Preskill, who had bet Hawking and won, who had prodded and provoked and encouraged for 30 years, and Hawking himself, dead since 2018, who had posed the question that had driven everything. The recognition came slowly, as scientific recognition often does. There were no Nobel Prizes, at least not yet. Theoretical physics without experimental confirmation operates on a different timeline, but within the community the achievement was acknowledged. The key papers were cited thousands of times. The authors were invited to give lectures at the most prestigious venues. Graduate students arrived hoping to work with the scientists who had solved the paradox. The island formula entered textbooks, first in draft form, then in polished editions that would train the next generation. The question, what happened to information in black holes, could finally be answered with something other than speculation. It was preserved. It emerged in the radiation. The calculations showed it. And yet, in the way of science, the resolution of one puzzle opened the door to others. If space-time was emergent, what was it emerging from? If entanglement could connect distant regions in ways that violated naive locality, what did this mean for causality, for the structure of physics itself? If the island formula was a window into quantum gravity, what lay beyond the window? What was the view it revealed? These questions did not have answers yet. They might not have answers for decades, or centuries, or ever. But they could now be asked in a new way, informed by concrete results rather than mere speculation. The community had been given a Rosetta Stone, a key to translating between the language of geometry and the language of quantum information. Learning to read this language was the task that lay ahead. In a small apartment in Cambridge, England, an elderly physicist who had known Hawking since their student days sat in a worn armchair, reading the latest papers on island theory. Outside, rain streaked the windows, a familiar English grey softening the edges of the old stone buildings. He had never worked on black holes himself, had spent his career on more practical problems, solid-state physics, superconductors, the behaviour of electrons in unusual materials. But he had always followed Hawking's work from a distance, had attended his lectures and read his books and marvelled at the audacity of the questions being asked. Now, holding the printouts of papers dense with mathematics he could only partly follow, he felt something like wonder. The question that had consumed his old friend, that had driven him to make claims that alienated colleagues and sparked decades of debate, had finally been answered. Information was preserved. Hawking had been wrong about the answer but right about the importance. The paradox had mattered, and the resolution had come from ideas that would have seemed like science fiction, when they were both young students bicycling through these same streets, arguing about physics and philosophy and the nature of reality. This was what science could do when given enough time and enough minds working on a hard enough problem. It could take a question that seemed unanswerable and through decades of patient effort, through wrong turns and dead ends and sudden breakthroughs, arrive at something like truth. Not absolute truth, science never claimed that, but a truth robust enough to build on, to extend, to test against the strange universe that had produced beings capable of asking such questions in the first place. The information paradox had been a crucible, a test of the entire framework of modern physics, and physics had passed the test. Quantum mechanics was intact. General relativity, suitably interpreted, was compatible with it. The foundations held. The rain continued to fall outside the window, as it had fallen for millennia, as it would continue to fall long after all the physicists were gone. Somewhere in the depths of space, black holes continued to form and evaporate, emitting their soft radiation into the expanding darkness. Each one carried within it the encoded history of everything that had ever fallen in, stars and planets, light and dust, perhaps even civilizations that had risen and fallen and left no other trace. That information was not destroyed. It flowed outward, scrambled beyond any practical hope of recovery, but present, mathematically recoverable, a permanent record written in the quantum state of the cosmos. This was what physics had discovered. This was what Hawking had set in motion 5 decades earlier, when he had sat down to calculate what happened when quantum effects were considered near a black hole horizon. The story of the information paradox was, in the end, a story about what human beings could achieve when they refused to look away from a hard problem. It was a story about persistence, about the willingness to be wrong and to admit it, about the transmission of questions from one generation to the next. It was a story about the strange universe we inhabit, which seems to have been constructed according to principles we do not fully understand but can slowly, painstakingly, partially discover. It was a story about the power of mathematics to reveal truths that intuition alone could never reach, and about the limits of that power, the questions that remained even after the calculations were done. It was a story about time, the time it took to solve the paradox, the time experienced by observers inside and outside black holes, the time encoded in the entropy and information of Hawking radiation. And it was a story about a man in a wheelchair, his body frozen but his mind ranging across the universe, asking a question that would outlive him, and that would, in the end, be answered by those who came after. Stephen Hawking died on March 14th, 2018, on what would have been Einstein's 139th birthday. He did not live to see the island formula, did not live to see the page curve calculated from first principles, did not live to see the paradox he had posed finally and definitively resolved. But in a sense he was present at the resolution, his work woven into every step of the argument, his questions animating every page of the papers that finally provided the answer. The young physicists who wrote those papers had grown up reading his books, attending his lectures, dreaming of someday contributing to the problems he had made famous. They stood on his shoulders even as they overturned his conclusions. This is how science works. This is how progress happens. The ones who ask the questions are not always the ones who answer them, but without the questions there would be no answers. The black hole information paradox is solved. This statement, which would have been controversial just a few years ago, is now the consensus view of the theoretical physics community. The details remain to be worked out. The deeper theory remains to be found. But the central question, whether information is destroyed in black hole evaporation, has been answered. It is not. The universe is stranger than we imagined, space-time more malleable, reality more interconnected. But it is also more coherent, more lawful, more comprehensible than it would have been if information were truly lost. We live in a cosmos where nothing is forgotten, where the past is encoded in the present, where the laws of physics preserve the bookkeeping of existence no matter how extreme the circumstances. This is a profound truth, one that speaks to the deeper structure of reality, and it was discovered by human beings, using mathematics and imagination and the accumulated wisdom of generations, working together across decades to solve a puzzle that once seemed impossible. In the grand tapestry of scientific achievement, this resolution will take its place alongside the great discoveries of the past, the structure of the atom, the nature of light, the expansion of the universe, the origin of species. It will be taught in physics courses for as long as such courses are taught, a landmark in our understanding of how the cosmos operates. And it will serve as a reminder that even the hardest problems yield to persistent effort, that even the most baffling paradoxes contain within them the seeds of their own resolution, that the universe, for all its strangeness, is ultimately comprehensible to minds that refuse to stop asking why. The rain stopped. A thin sliver of sunlight broke through the clouds over Cambridge, illuminating the old stone and the new glass, the ancient towers and the modern laboratories, where the next generation of questions was already being formulated. Somewhere out in the darkness between the stars, a black hole continued its slow evaporation, hawking photons streaming outward at the speed of light, carrying their burden of information toward a future no one could predict. The universe kept its secrets, but it also kept its records. Nothing was lost, nothing was ever lost, and in that preservation, in that perfect quantum bookkeeping, there was something almost like memory, almost like meaning, almost like hope.